Alright, so today I'm gonna be talking about Barlow Twins, self-supervised learning via redundancy reduction. Sometimes you don't need a sophisticated contrastive network. You can just use this paradigm of this model of Barlow Twins. And it's very simple, very, very simple. The implementation is very fast, very simple. And of course, there are very few theoretical explanation, but it's very fast. I want to explain this article in 2021. So self-supervised learning is rapidly closing the gap with supervised methods on large computer vision benchmarks. A successful approach to self-supervised learning is to learn embeddings which are invariant to distortions of the input sample. However, a recurring issue with this approach is the existence of trivial constant solutions. Most current methods avoid such solutions by careful implementation details. We propose an objective function that naturally avoids collapse by measuring the cross-correlation matrix between the outputs of two identical networks fed with distorted version of a sample and making it as close to the identity matrix as possible. This causes the embedding vectors of distorted versions of a sample to be similar while minimizing the redundancy between the components of these vectors. The method is called Barlow Twins owing to neuroscientist Barlow. So Barlow was a neuroscientist and he was working on redundancy reduction principle, and so they applied to a pair of identical networks. Barlow Twins does not require large batches nor asymmetry between the network twins, such as a predictor network, gradient stopping, or a moving average on the weighted updates like SimSiam and BYOL that we have talked in the previous lectures. Intriguingly, it benefits from very high dimensional output vectors. Barlow Twins outperforms previous methods on ImageNet for semi-supervised classification in the low data regime and is on par with current state-of-the-art for ImageNet classification with a linear classifier head and for transfer tasks of classification and object detection. The good news is you don't need large batches, you don't need gradient stopping, you don't need momentum encoder, those exponential moving average that in algorithms like SimSiam and BYOL we were talking about. You don't need predictor network like the algorithm of BYOL. So this is the architecture, so simple. You just create this matrix empirical cross-correlation and you see everything is very simple, symmetric. You have encoder projector for the distorted images. So until here is just the augmentation and the rest of that is very simple. So like other methods for self-supervised learning, Barlow Twins operate on a joint embedding of distorted images. More specifically, it produces two distorted views for all images of a batch sampled from a dataset. The distorted views are obtained via a distribution of data augmentations. The two batches of distorted views are then fed to a function f theta, typically a deep network with trainable parameter theta, producing batches of embedding ZA and ZB. To simplify notations, Z sub A and Z sub B are assumed to be mean-centered along the batch dimension such that each unit has mean output 0 over the batch. So Barlow Twins distinguishes itself from other methods by innovative loss function. So the first term is called invariance term. The second term is called redundancy reduction term. We want to reduce it as much as possible. We don't want redundancy. So lambda is just a positive constant trading off both worlds. The first world is the first and second terms of the loss, and C here is just the cross correlation matrix. And you can compute the components of this matrix using this equation 2. So B here, as you see, B, all of the are indexes batch samples. And I and J here is just the index, for example, Cij is here. C11 is here. C12 is here. So it's a matrix of cross correlation. So the first term is very important, invariance term. The invariance term of the objective, by trying to equate the diagonal element of the cross correlation matrix to 1, makes the embedding invariant to the distortions applied. The redundancy reduction term, by trying to equate the off-diagonal elements of the cross-correlation matrix to 0, decorrelates the different vector components of the embedding. This decorrelation reduces the redundancy between output units so that the output units contain non-redundant information about the sample. More formally, Barlow Twins' objective function can be understood through the lens of information theory, and specifically as an instantiation of the information bottleneck. Applied to self-supervised learning, the IB, that information bottleneck objective, consists in finding the representation that conserves as much information about the sample as possible while being the least possible informative about the specific distortions applied to that sample. So it has similarities with existing objective functions for self-supervised learning. For example, the redundancy reduction term plays the role similar to contrastive in the info and C, this popular objective function. However, important conceptual differences result in practical advantages of our method compared to info and C. So this is the PyTorch pseudocode. First, you load batch with n samples. You get the two randomly augmented versions of X like any other algorithm. Then you normalize representation along batch dimension. After that, you just calculate this matrix Cij. You calculate all the components using this cross correlation matrix. So MM is matrix multiplication of ZA norm and ZB norm. And the loss is just C minus the identity powered to the 2. And you have the loss, and then you back propagate. So it's very simple. And for image augmentations, each input is transformed twice to produce the two distorted views. So it consists of random cropping, horizontal flipping, color jittering. But in the world of NLP, we have many difficult problems. The encoder consists of a ResNet 50 network, and the projector has 3 linear layers, each with 8,000 output units, because they promote higher dimensions in this Barlow Twins paradigm for some theoretical reasons. And for optimization, they follow just the BYOL that I've explained. We use Lars optimizer and train for 1000 epochs with a batch size of 2048. Very big batch size. We, however, emphasize there are other works with batch sizes, so you can also use as small as 256 is enough. Learning rate is just 0.2 for rates, and the smallest one is this one for biases and batch normalization parameters. And we multiply learning rate by batch size and divide by 256.